Okay, welcome. Let's get going. The bad news is I only have 15 minutes. Sorry, 30 minutes, which is not enough to explore this subject. So I'm going to have to ask you to keep up with me, and if we don't get through it all, come and ask me about the rest of it afterwards. The first thing I did when I got this was change my lanyard for an arm lanyard. So you're at a proper conference now. How many of you have actually worked knowingly on a platform that has some ARM technology in it? Okay. Most of you. How many of you have a phone? Mobile phone? Right, okay. You've used ARM technology. So we're okay. We'll have to get the rest of you moving on to ARM technology properly. But okay, the subject I have today, memory access ordering in complex embedded systems, because embedded systems, what passes for an embedded system these days, something like your typical mobile phone, is getting increasingly complex in terms of the hardware design, the microarchitecture, the way things work inside and outside the processor. And one of the places that really becomes obvious is when you look closely at the order in which accesses happen to memory, and you compare that with your program and what you actually wanted to happen. And frequently what you wanted to happen doesn't. I first sort of came across this subject or realized what a complex subject it was on one of the forums on LinkedIn. I don't know whether any of you use LinkedIn, Facebook for professionals or Facebook for grown-ups if you want. And some of the forums in there, occasionally you get a really interesting conversation springs up. This one was from the Embedded Forum. And someone sort of cross-posted from one of the other forums, from one of the RTOS groups, a really simple question. And the question was this. It was, is there any guarantee that two sequential writes to two volatile variables will be executed in the same order as they appear in the code? And the discussion went on and on and on. And we had compiler writers, we had system designers, we had RTOS people, we had system architects, everybody. And it went on for several hundred posts in this conversation, well, the longest I've ever seen. And it started, you could see it starting to dawn on people as the conversation went on, that the answer to that question, simple though the question is very often no. And that comes as quite a shock to some people. And you could see the shock starting to dawn on the conversation as people realize that actually, no, you can't guarantee that. And volatile is not enough, if you like. And there are a huge number of issues kind of buried away in that question and in the answer. And a lot of people working on embedded systems, on simple embedded systems that are getting more complex, don't realize that these issues are starting to happen. And you really have to know what's going on and take note of it and take account of it when you're writing your code. So let me give you a little trip down memory lane. Nostalgia, it's a complex English word there, you know what it means. Nostalgia is love of the past, if you like. So we have a saying, nostalgia is not what it used to be. And the same is true of the embedded industry, if you like. It used to be very, very simple. And most things in the industry have got hugely better in the last few years. I've been around the embedded industry for about 30 years now. And when I first started out, we were developing code for a radio network switch operated console. It was a touchscreen console that communicated over a serial line with a telecommunications switch. And it was a custom board that we designed around a 6809 processor, if you remember those. And we cross-compiled the code on an IBM PCXT. That really dates me. It had twin floppy drives. 5.25-inch floppy drive. So you put your source code on one disk and the editor on the other, and you put both of these in, and you ran the editor and edited your source code. And when you were happy with it, you took the editor disk out and you put the compiler disk in. And you compiled your code. And if it compiled properly, then you took your code and you generated a binary image from it, and you put that into a PROM programmer, and you programmed it hard into UV erasable PROMs that you'd cooked in a UV chamber. And then you plugged those physically into the board and you pressed reset and you would sort of see what happens. And the company couldn't afford an emulator, so we had to debug everything using printf and a serial port. So that's how hard embedded development used to be. Believe me, some of it was very hard. Things have got so much better in that sphere. So we now have on-chip debug over JTAG. We now have machines with 500 terabyte hard drives, so you don't have to worry about changing disk drives all the time. So some things have got a lot easier. But those old systems that I certainly and most of us used to work on, It used to be very simple because they all conformed to what is called the sequential execution model. The system was really simple. And the bus, if you like, it was kind of simple, it was dumb, it was single layer, it was in order. And unless you had external sort of wacky components like DMAs, the only thing in the system that was capable of driving the bus and driving memory traffic was the processor. And the processor was really in total control of everything. And if you looked inside the processor, that was neat and tidy too. Most of these processors didn't have pipelines, so there wasn't much parallelism going on. If they did have a pipeline, it was very simple. Instructions were issued in sequence, they were executed in sequence, they were retired in sequence. And everything issued to completion, including side effects and memory excesses, before the next instruction came in. So everything was beautifully in order. And that sequential execution model applied at kind of every level in the system, from instruction fetches right through to memory accesses, internal control operations right through to peripherals. And life in that respect was very, very simple. So you only really needed to know a couple of things to ensure that things happened in the right order. And you had to know that sometimes actions on a peripheral in the memory system took a little bit of time to complete. So once you initiate something, you might have to poll for its completion, or perhaps you'd set an interrupt to wait to track that completion. And the second thing was that you had to tell the compiler that some memory locations did not behave normally. So some memory locations corresponding to memory map peripherals kind of had a nasty habit of changing when you weren't looking at them. And the way you did that was using the volatile keyword. Now, I'm sure you all use volatile, you know what it means. And memory locations like that, which are sensitive, which have a habit of changing when you're not looking at them, you declare them as volatile. And then the compiler turns off some optimizations, and you can see on the screen very simple example of that. We're just reading a pointer twice, declare it as volatile, and you can see that the code down there, bottom right, actually physically reads that location twice. The code at the top left just optimizes out the reads completely, because the compiler doesn't know, unless you declare it as volatile, that this location might change, so it has to read it. Now, this only affects the behavior of the compiler. If you declare a variable as volatile, that's not visible to the processor. It's not visible to any part of the system at runtime. It just has an effect on the code that is generated by the compiler itself. And if the system doesn't behave the way the compiler expects it to, then potentially you have a problem. And unfortunately, that's exactly what a lot of modern systems do, the kind of systems we work with these days. Because these systems try to be so clever, they try to optimize things, to maximize throughput and so on, they end up doing things that the compiler doesn't expect them to do. And you really notice this more than anywhere else when you look at the order of accesses to memory. Because a modern system now looks like this. This is the kind of system you get in an awful lot of embedded systems. In almost any phone or tablet these days, you get a system like this. You've got multiple processors. You've got memory coherency hardware. You've got a multi-layer, multi-master bus matrix. You've got intelligent peripherals that are capable of initiating independent bus transactions separately from the processor. You've got semi-autonomous subsystems that are hiding behind bridges, and you have to deal with this. And if you look at the kind of things you might have to deal with in a system like that, say you've got multi-core processors. They might be running symmetric multiprocessing. They might be asymmetric. They might be multi-threaded multiprocessing. You've got processor execution pipelines that are very, very clever. And in order to maximize instruction throughput, they do things like speculative instruction fetch, speculative execution, multiple issue per cycle, out-of-order issue, out-of-order completion. All of these exist today in ARM processors that are very, very widely used, and many other architectures too. Then you've got multiple levels of cache, so it's not always obvious where the most up-to-date value for a particular memory location actually is. Is it in L1 cache that's private to me? Is it in L2 cache, which is shared? Is it in L3 cache, which is somewhere sort of out in the bus matrix and visible to other subsystems? Even when an item is in a particular cache and you can identify it, maybe you've got cache coherency management hardware that's automatically making sure that some subset of the system components have access to the right value. And that makes tracking these values sometimes a little bit more difficult. Then you've got memory interfaces that try to optimize bus traffic by doing things like merging memory accesses. So if you write the same location twice, the bus matrix may look at that and think, no, there's no point in doing the first one. It actually collapse the two into a single write and just write the second value, because there's no point in doing the first one, right? Perhaps a location that's just been read can be cached in some local cache system to avoid subsequent bus accesses and reduce bus bandwidth. Two separate accesses that maybe update two adjacent half words. Maybe the load store unit can actually merge those into a single word access and actually only carry out one bus transaction. If you don't know these things are going on and you don't know how to stop it, it can really start playing tricks with you. Then you have multiple bus layers and multiple bus masters. So accesses that used to be atomic are actually not atomic anymore at the bus level. And that can increase the latency of individual transactions too, because other masters can get hold of the bus and maybe hold it for quite a long period of time. So all of this is available on something of the character of a mobile phone these days, and a complex embedded system has all of these. So that sequential execution model really doesn't apply anymore, and you kind of have to come to terms with that new reality. And the hardware isn't the only thing that's changed either. Compilers have got a lot cleverer too, and the optimizations that compilers carry out are a lot more complex. So we don't have time to do much more than really kind of scratch the surface of some of these issues. So, volatile keyword. There's a simple piece of code there that declares two hardware registers, one called control, one called status. And like a good programmer, this guy has declared both of these as volatile. But is that enough to ensure that the device is reset before it's accessed, right? So presumably, on the code up there, writing 1 to the control register resets the device. So you have to be sure that that's complete before you read back the status register. Otherwise, you might get unpredictable behavior. Now, does declaring those items as volatile guarantee that the peripheral out in the memory system sees the write to the control register before the read from the status register? Okay, you should be ready for the answer to that by now, and the answer to that is no. And there's at least two reasons for that. First one is the compiler, because the compiler can reorder memory accesses as long as it does not change program behavior. So if the compiler were to exchange the accesses to control and status, as far as it's concerned, program function is maintained. It's not affected at all. So it can do that. They're independent variables. Sometimes the compiler will do that. Some compilers will, actually, and some compilers won't, because the C standard is deliberately silent on a lot of issues, and this is one of them. And one of the issues that it's silent on is the compiler writer free to reorder accesses to volatile variables. So the guy who writes the compiler can actually make it up on this one, and you can't rely on what decision he or she has actually taken. Second reason is down to the hardware. The write to the control register maybe goes through a write buffer, could stay there for an indeterminate length of time, and the read from status might be satisfied by some local cache, so it means it's much quicker to read status than it is to write control. And as far as the processor is concerned, they're completely independent variables. They have different memory addresses. So there are no visible data dependencies, so the load store unit, or the pipeline, is free to process those actually in any order it likes. So this code provides no guarantee that that peripheral will be accessed correctly, which is actually rather depressing. I say, and a little bit more depressing when you realize that the compiler and the hardware both kind of conspire to do this. Just a little recap here on the other use of the volatile keyword. In this example here, you have to declare the variable status as a volatile variable because it can be changed by an interrupt handler. So when the main loop isn't looking, it might get changed in the background by the interrupt handler, and you have to declare it as volatile so the compiler doesn't try to cache the value in the foreground loop. And if it did, your program wouldn't work. So both of these cases I'm hoping you're familiar with. That they illustrate an important point. And that point is that neither the compiler nor the hardware actually have enough knowledge about the intended program behavior and the behavior of the system, the target system, to guarantee that your program will actually do the right thing. Certain memory accesses have side effects, and certain memory accesses may be linked to each other in a way that the compiler and the hardware cannot see, right? And thirdly, in this sort of desperate desire to help you out and run your code as quickly and efficiently as possible, the compiler and the hardware make optimizations which they regard as safe, but they can affect program function in situations like this because the compiler and the hardware are missing key information. You're the programmer, you have that information, and you have to pass it on somehow. So let's look a little bit deeper. Let's look at a detailed operation of a processor pipeline. If you remember college courses on microprocessor architecture, pipelines are really very simple. These days they are not. In the kind of processors that you find in even a simple mobile phone these days, you find astonishingly complex pipelines. They're very long, much longer than they used to be. The example on the slide is only 6 stages long. The pipeline in a Cortex-A57 processor, it's a 64-bit ARM processor, which is going into the top of the range smartphones these days, has a pipeline that is 15 to 18 stages long. So there's a lot of complexity here. And the potential for the processor doing something inadvertently that you didn't intend is huge. With out-of-order execution, out-of-order completion, a lot of speculation going on. But don't think, or don't go away with the impression that this sequential execution model has gone completely out of the window. It hasn't. It does still hold, and it has to. The compiler and the hardware have to ensure that it does, but only at the kind of the local level. This processor, this pipeline, this memory interface, running this code right now. The sequential execution model has to hold. Okay? It's when you extend that beyond the immediate context in which you're running things that the things start to go wrong. These things that help you, just remember, sometimes they don't quite do that. So let's look at a really simple example. This is how a modern pipeline might affect the order of memory accesses. What the pipeline is trying to do is maximize instruction throughput. It's trying to help. So you have some source code, which is on the left there. It compiles to some instructions on the left. And you can see that there's a store and a load. And the store happens before the load. Now, if you put that through a simple in-order processor with an in-order pipeline, you might get the sequence in the middle. And the instructions are issued into the pipeline cycle by cycle in the order they occur in the program. And if you ignore things like write buffers and caches, which are kind of outside the pipeline, then you can assume, as you see, that the store is executed before the load, and assuming that there are no load store unit effects, the store will actually complete before the load does. Now, if you put that on an out-of-order superscalar pipeline, like you find a lot of processors, you might get the sequence that you see on the right there. And to hide the latency of the multiplier, you can see there's a stall in the sequence here. So to get rid of that, and to hide it, what the pipeline has done at runtime is promote the load up the sequence and actually issue the load before the store. It also hides the latency of the load as well, because you can see there's another stall down here. And both those stalls have disappeared because the latency of the load is now hidden under the store, and the latency of the multiplier is hidden under the load. Okay? So the pipeline's done something really clever here. It's done something you want. It's increased the efficiency and throughput of your system. But it has done something you perhaps didn't want it to do. It's executed the load before the store. And remember, right back to the beginning where we had that example with 2 variables, control and status. Here is an example of how the pipeline might, at runtime, reverse those 2 operations. Right? You have no control over this, really. You can't tell the pipeline, don't do that. So that you have to find some way of getting that information to the system. Don't reverse these. Okay, because they are linked in some way. So I'm going to use ARM systems to illustrate how a modern complex embedded system gets around these issues. I make no apology for using ARM systems. I work for ARM, so that's what I'm going to talk about. But don't forget, you need this behavior. This behavior is what makes systems as efficient and powerful as you need them to be. So there's a couple of ways that we use in the ARM architecture, other architectures have similar mechanisms, to get this information into the system at runtime. Because remember, it's needed at runtime. Because this behavior happens in real time. It happens when you're not looking. If this causes a bug, it's what my lovely friend Hubert there calls a Heisenbug, which means when you try and look at it, it goes away because it's very timing dependent, it's context dependent. As soon as you alter the timing and behavior of the system by observing it, this kind of thing goes away, or it may go away. And it may not fail first time you run it. It may fail the 1,000th time you run it or the 1,000,000th time you run it because it depends on real timing on a real system. So we have a couple of mechanisms in ARM systems. And the first one is memory types. That every addressable area of memory in the system has to be assigned a memory type. I'm not really concerned with how you assign these. It varies from system to system, but basically you program this into a memory management unit or a memory protection unit at runtime. You program this into the system. It's not something you tell the compiler, it's something you tell the system. And ARM systems have recognized this for about 10 years now, since ARM version 6 of the architecture. So the vast amount or the vast quantity of memory in your system is going to be what we call normal memory. And that's exactly what it says. It behaves normally. So the key element is that memory accesses to normal memory do not have side effects. Okay, so the compiler and, in fact, the system is free to carry out a whole ton of optimizations. It's allowed to speculatively access normal memory because those accesses don't cause anything else to happen. Okay, it can do that as much as it likes. So it can carry out speculative instruction fetches, speculative cache fills, all kinds of things. It can merge, reorder, resize, repeat, cache, and buffer. Right? Now you can see every single one of those has a potential effect on the number and order of the accesses that are actually happening. Most memory in a system is normal because your normal RAM, your normal data structures, all your code memory actually has to be normal. The ARM architecture requires that. And there's a second type of memory that we use for device memory, and surprisingly enough, that's called device memory. In device memory, the key thing is that accesses may have side effects. So the machine is not free to speculatively access device memory because every access you make to a memory-mapped peripheral region may have a side effect, and you have to manage those side effects. So you can't let the hardware go accessing this stuff. It also has to maintain size, order, and number of accesses, so it can't repeat things, it can't speculatively access, you can't cache device memory, you can use write buffers, but again, you might have to manage those a little bit carefully. So this memory you use for memory map peripherals and some system registers. There's a third type of memory defined in the architecture called strongly ordered, which is really nasty stuff. We defined it as incredibly strict ordered memory for legacy reasons, but then discovered that no one used it and no one could really work out what it was for. So we've actually dropped that in the latest versions of the architecture. So you don't need to worry about that one anymore. The second thing we have is the concept of memory barriers. Now, all architectures, all complex architectures have a similar concept. These are instructions that you insert into your instruction stream to manage memory ordering. PowerPC has the fantastically named enforce in order execution of I/O, EIEIO instruction, which is a really good one. But other architectures have things like fence instructions. PowerPC, I think, has fence instructions. So these barrier instructions allow you to enforce ordering. And we have three types, DMB, DSB, and ISB. And they kind of vary in strictness, and they vary on which interface they affect. The first one, the most common one, DMB, stands for data memory barrier. And that just ensures that all memory accesses before the DMB instruction complete, before any memory accesses after the DMB instruction are initiated. So it's kind of a checkpoint. It says, don't initiate any more memory access until you've finished all the ones that happened up to now. Okay? You can do other stuff. You can execute data processing instructions. You can execute control flow. You can do anything you like, but you can't access memory until you've finished everything else. There's a slightly stricter version called the DSB, data synchronization barrier, which actually stalls the processor at the DSB instruction until all outstanding memory accesses are finished, and then it carries on. It won't let it do anything else at all. There are some examples where a DMB is not quite strict enough, so you need the DSB. And the final one there is an ISB, is an instruction synchronization barrier, and that causes the instruction pipeline and all the prefetch buffers and all the speculative fetching that's going on to be emptied out and refilled. So it's kind of a context synchronization, if you like, on the instruction side. And it's the sort of thing that you do as part of an OS context switch, or if you've just enabled a coprocessor, or you've enabled something that changes the way that instructions execute. You execute an ISB, flushes everything out, resets the instruction decoder, if you like, and then off we go again. ISB, you tend to see those in operating system context switches. And here's an example of a case where you may need a DSB because it's slightly stricter than the DMB. So this is a sequence that you might get at the end of an exception handler. So we've got a store here that writes some peripheral register to clear the interrupt down. And then this last instruction here, that's return from exception. Now, return from exception isn't a data access instruction. It's not a memory access instruction. It's a control flow instruction. And it has control flow elements and some stack access with it too. But it can be initiated before the memory accesses start. So without the DSB here, this access here may not actually complete or be issued from the memory system before you start the return from exception process. That's a bad thing because if you haven't cleared the interrupt down properly, you then go ahead and return from the interrupt, you're just going to get re-interrupted again. So here, the DMB is not enough because the RFE could be initiated before this access is finished. DSB actually makes the processor stop, wait, finish that access off, and then continue. Okay, what we talked about so far, there's another example here. These are slightly more complex examples, which I don't have time to go through properly today, where you've got interactions here between data context and instruction context, and we're doing things like changing the way that the memory address decoder works, and here we're changing the branch prediction system. And invalidating memory addresses which are cached as part of the memory translation and as part of the branch predictor system. So I don't have time to go into those today, unfortunately. Then let's introduce a different situation. Let's introduce a second processor into the mix. So I've got two processors here, processor 1, processor 2. Now, in a kind of nice, neat, ordered, tidy view of the world, if processor 1 updates variable x and then updates variable y, and processor 2 reads variable y and then reads variable x. Now, you can make some good assumptions about that, or you should be able to. You should know that there are only 3 possible outcomes. Right? If processor 2 reads the 2 variables after processor 1 is finished, then you would see the new values for both. You see new x and new y. If processor 2 reads y in between processor 1's 2 updates, then you'd see new x and old y. If processor 2 reads both before processor 1 even starts, then you see old x and old y. Now, there's one combination there, new y and old x, which you should never see. So you might think you're safe to build your code around the assumption that that situation will actually never happen. Now, unfortunately, that's not true. And you should be able to kind of put together some of the ideas that I've been through to work out how that happens. Here's a simple sequence, for instance. In that example there, in what order are A and B loaded from memory? The instruction to load A comes before the instruction to load B, right? So you'd think it would load A before load B. But what if both of them are cacheable, but the load of A causes a cache miss? What if A is cacheable and B is not? What if A is not cacheable and B is? All of those situations can change the order in which those memory accesses are actually satisfied. If your cache is complex enough to be non-blocking and carry out hit under miss behavior, then if the load to A causes a miss, the load to B can be satisfied immediately, and you can see that those values can then be loaded in a different order, and that illegal combination that we identified on the previous slide can occur in a multiprocessor system because one processor is changing your data and you're reading it in an order that you weren't expecting. So your program has to be actually built to cope with that. Another thing so how do you deal with things like this? Well, you have to come up with some kind of lock structure to deal with what we call critical sections. And I'm sure if you've done sort of OS programming, certainly multitasking OS programming, you'll be familiar with the need to protect critical sections from access by 2 threads or 2 processors or 2 bus masters at any particular time. So you need some kind of lock structure here. Now, if you look at that sequence, you look at it afterwards if you like, you can see that that lock structure almost certainly wouldn't work because it relies on something which should be atomic but isn't. And so we need some help in the bus system to actually make that happen, to actually make a load and a store into an atomic operation. Now, you can do it using a sort of old-fashioned technique, which we used to use in the ARM architecture called a swap instruction, which actually locked the bus between a load and a store. That doesn't scale to the kind of complex system that we're looking at these days because you can't lock a complex bus for that long. You can't lock a multi-layer bus for that long, feasibly or scalably. So instead, we introduced a couple of new instructions, load and store exclusive. And what a load exclusive instruction does is it loads just like a normal load does, but then reserves that location for what we call exclusive access. And then a subsequent store exclusive instruction stores to the address, but also checks the reservation. And if the reservation is still there, it returns success. If somebody else has changed that location or stored to it in the meantime, then that store will return a failure, and you'll know that your attempt to actually get that lock didn't work. So it's a way of linking a load and a store and making them a kind of pseudo-atomic operation, if you like. There's an example which, again, I'll leave you to run through afterwards when you get hold of these slides or watch the video. I'll leave you to work through that, and you can see that on the left-hand side here we have a lock sequence that uses a load and store exclusive to carry out an atomic load and store of a lock location. And it just loops round if somebody else has changed that location in between the load and store exclusive instructions. The unlock on the other side is very simple. You can just use a simple store, because one side effect of a store is to clear the reservation, so everybody else gets informed that you've actually changed that variable. So I'm just running out of time, but I only have a couple of slides left. Really just to summarize the memory access ordering issues that you need to start taking account of when you work with a system this complex. And these systems are very, very common these days. So here's a list of things you need to care about. Memory ordering. When you need to ensure that 2 memory accesses or 3 or 4 memory accesses occur in program order. This is where you use either the concept of device memory to ensure ordering, and you also need to insert these memory barrier instructions. You can insert those into C programs using either little bits of inline assembler or using compiler intrinsic functions. The compiler will not put them in for you, right? The compiler doesn't know about any of this stuff. Then you need cardinality. This says when I've written 3 memory accesses and I want exactly 3. Okay, I don't want the compiler or the memory system to go merging these or resizing them or doing anything. I don't want that, so I want 3 accesses. Volatility, that's the most common one, the one we started with, when memory locations have a habit of changing when you're not looking. This is the common use of the volatile declaration. Memory access completion is a little bit more difficult. I need to know when that access is completed. And again, you can see the part that barriers play in that. Barriers allow you to put checkpoints in code that allow you to be ensured that certain memory accesses have completed either before you start other ones, that's DMB, or before you do anything else at all, that's DSB. Observability is a little bit more complex, subtly different. An access completes when it sort of leaves your sphere of influence. So it completes, if you like, when it sort of goes out of the load store unit or goes out of the write buffer. An access is observed when a separate processor in the system can see the result of that access. So it's actually reached an area of shared memory or an area where other people can look at it. And then finally, atomicity, which is really, really hard. You need to know that a series of memory operations are carried out in a single uninterrupted sequence that's indivisible. This is very hard to deal with sometimes. The lock structures that I've shown you using load and store exclusive instructions, there are some other variants on those instructions in the latest version of the architecture, and they kind of give you the ability to manage atomicity in a very, very controlled way. But you need to know the architecture well too. For instance, word accesses to word-aligned variables are atomic in the ARM architecture, that's guaranteed. But what about a word access to an unaligned address? Is that atomic? Sometimes it is, sometimes it isn't. Okay, and if you care, you need to read the architecture very carefully and find out. What about a double word access that crosses a bus boundary? Is that atomic? No. If it fits into a single bus boundary, single bus transaction, then it is. But what is the size of that bus transaction? Answer, it varies from processor to processor. So there's a lot of issues that you need to bring into play there. And all of this, say, has its own completely incomprehensible chapter in the ARM Architecture Reference Manual, which I would encourage you to go and read when you need to go to sleep sometime. So, okay, just winding up here. I'm afraid I like to introduce a little bit of culture into our terminally uncultured industry, which is why I was so pleased to see that fantastically arty keynote, which is one of the best keynotes I've ever seen. But there's so many questions here, and there's so little time, and I've run out of it already, and I'm running into your coffee break. I'm sorry for that. You'll have to run for your coffee. We just don't have time to go into this. And what that reminds me of is when the story of the discovery of Tutankhamun's tomb in Luxor in the 1930s. And the guy who discovered it, Howard Carter, when he sort of broke through the seal on the door into the innermost tomb that nobody had been into for 3,000 years or whatever, he wrote this in his diary. And he said, "As my eyes grew accustomed to the light, details of the room merged slowly from the mist. I saw strange animals, statues, and gold. Everywhere the glint of gold. And for a moment, it must have seemed an eternity to others standing by. I was absolutely dumb with amazement." And Lord Carnarvon, this is the guy who was bankrolling him, unable to stand the suspense standing behind him, said anxiously, "Can you see anything?" And it was all I could do to get out the words, "Yes, wonderful things." And I hope for you, this session has been a little bit like just opening the seal on the door and going, wow, there's some serious stuff in here. And there's some stuff that we seriously need to get hold of. And say, on my mission to increase the culture level of our industry, two quotations I want to leave you with. This one is literary, nice arty. It's Marcel Proust, À la recherche du temps perdu. He says, the remembrance of things past is not necessarily the remembrance of things as they were. Human memories are fallible and imperfect. Memories on complex embedded systems are clever and very, very clever. Sometimes a little bit too clever, and you need to get very clever with them in order to use them properly. But I like this quote much better. This comes from Lewis Carroll's Through the Looking Glass, and the Red Queen says to Alice, "It's a poor kind of memory that only works backwards." Anyway, thanks for your attention. There's a bucket labeled awesome. Please use it. Thank you.